start off today with something called the inverse function theorem. And so this is something that if you've taken a class in analysis, if you've taken 131 before, then you've seen this before. Let me recall or introduce to you the first the real value version that you have seen before, that you would have seen before if you've taken 131, real value version. Okay, so here it is. You have some function f on some region in R2, and it is continuously differentiable. Okay. So he is a subset of R2, and if the determinant of the derivative. So remember, the derivative is that matrix, is that linear transformation, right? Given by the Jacobian matrix. So if the determinant of that is non-zero, then your function is basically locally invertible. Okay. So then your function is locally invertible. Function is locally invertible. Okay, more precisely, then there exist neighborhoods U containing x naught y naught and V containing f of x naught y naught, such that when f, if we think of f going from U to V, it's a one-to-one onto map. F is a one-to-one onto map. It's a so-called bijection. Okay, bijection, one-to-one and onto, and thus has an inverse. Further, that inverse, f inverse, is differentiable. And third, the derivative of the inverse at the appropriate point is 1 over the derivative of the original function. Right? You know, sort of as that sort of thing you've seen before in one variable calculus. But right. So as long as the determinant of the derivative is non-zero, then your function has a local inverse function. Okay. So the way to think about this is, with that linearization, right? Your function, the way your function f of xy is basically f of x naught y naught plus the matrix times the change from x minus x naught y minus y. Right. Right. So if the determinant of this is non-zero, then this is an invertible matrix. Right? This is an invertible matrix, and all you've done is add something and multiply something by an invertible matrix. So you can invert that. You can invert that. Right? You can invert that at least for a short period of time where this is good enough. Right? Where this approximation is good. Okay. But if the determinant is zero, then what that's saying is that some collapsing occurs, right? That that the matrix collapses, right? Collapses. Right? Remember that the determinant of the matrix tells you how the matrix expands volume, right? So if the determinant is 0, then basically your matrix takes a small box and collapses it down to 0 volume. Maybe it flattens it, or maybe it collapses it down to a point. Okay. So such a thing is not invertible, right? Okay. So that's your intuition about it. Okay. So this is the inverse function theorem. And then if you want to think about it, think about the complex case. So in the complex case, if say that f is complex differentiable from E to C again, and that f prime is continuous. Right? We need the f prime continuous so that it will be continuous. We have this continuous differentiable thing. Okay. And say that f prime d naught is non-zero. Okay. So suppose that the complex derivative is non-zero. Right? We saw last time that this means that if it's differentiable, then in that case, f is real differentiable, and the determinant of the derivative is the absolute value is the modulus of this squared. Remember, right? And so by the inverse function theorem, by the real inverse function theorem, we know there exists an inverse, right? There exists a real differentiable local inverse. Okay, so we just apply the previous theorem, right? And say, well, we know that there's a real differentiable local inverse. Okay? So the only thing is that real differential local inverse complex differential? Is it complex differentiable? And so what we need to check is it suffices to check that the Cauchy-Riemann equations are satisfied. So, and this actually turns out to be a triviality. Okay. So remember that the derivative is going to be this d sub x, d sub y, d sub x, d sub y. The derivative of f, right, is this matrix. Right? The derivative of f is this matrix. Well then, right, the inverse function. The derivative of the inverse function, right, at f of xy is going to be 1 over the determinant of, is going to be the 1 over the determinant of f prime times dy negative dy negative dx dx. Right? Because you know what the derivative of a 2 by 2 matrix is, right? The derivative of a 2 by 2, like ABCD. I'm sorry, you know what the inverse of a 2 by 2 is, right? The inverse of a 2 by 2 is just going to be dA negative B negative C, 1 over the determinant of that. Right? So you take the inverse matrix. That is going to be the derivative of the inverse function, right? And all we have to do is check that this matrix is of the right form, right? We need this to equal this, right? Like to satisfy the Cauchy-Riemann equations just means that this entry and this entry must be equal, and this entry and this entry must be negatives of each other. But of course they are, right? Because this entry and this entry were equal, and we just switched them. And this entry and this entry were negatives of each other, and all we've done is multiply them by negatives, right? So they still satisfy the Cauchy. So the entries of the new matrix still satisfy the Cauchy-Riemann equations, right? So since we know this, and thus Cauchy-Riemann equations are satisfied. And so whenever you have a complex differentiable function whose derivative is non-zero, you have a complex differentiable inverse function, a complex differentiable local inverse. Okay, so it's just an immediate consequence of the real inverse function theorem, plus a verification that the inverse function's derivative actually satisfies the Cauchy-Riemann equations, which is straightforward. Christian?
What do you mean by, what does it mean for a complex function to be real differentiable? Are you just going under that interpretation of, the imaginary part is the x-coordinate, or the real part is the x-coordinate of the imaginary?
That's right, that's right. So you think of it as a function on the real, yeah, and then differentiate it, is it differentiable as a real function? Yeah, and so we had this theorem last time that a function is complex differentiable if and only if it's real differentiable and it satisfies the Cauchy-Riemann equations. And so that's what we're using here. Okay, any questions? It's actually just an immediate consequence, just immediate consequence of this plus a small verification. Okay, any questions? No? Locally. So just that, remember over here we said that there are these inverses. There are these neighborhoods U and B. It wasn't the whole plane. It was just there's a small place around. So you know that f prime of x naught y naught is non-zero, right? So at some x naught y naught, you know that here's f of x naught. So the derivative is here. The derivative here is non-zero, but maybe somewhere far away from here, somewhere away from here, the derivative is zero everywhere. Right? Over here, the function's not going to in that place the function's not going to be not going to have a local inverse. But near, you're guaranteed that there's a neighborhood around here and a neighborhood around here on which there exists an inverse function. So a local inverse, but not a global inverse. Okay. So should I read that up? An analytic function. Continuous. And later we'll see that we don't need this, that this, once it's analytic, automatically f prime will be continuous, because as we'll see later, f being analytic means that it's infinitely differentiable. Okay, so we don't really need to include this condition. If f prime is non-zero, then there exists a local analytic local inverse f inverse such that whose derivative behaves as an opposite. Right. The derivative of the inverse of the red point is 1 over the derivative of the original function. It's saying exactly the same thing as the previous one. Okay, but just we now have the word analytic instead of differential. Okay, so okay, let's get back to harmonic functions. And we're actually not going to talk that much about harmonic functions. We'll talk a little bit. Okay, so recall, we said you have some subset of R2, and you have a function, a real value function, satisfying this differential equation, right? Which we abbreviate delta u, the Laplacian of u is 0. Okay. Such a function is called a harmonic function. And recall also that we noted that if f is analytic, then both u and v are harmonic. Right? There's the real part of f and the imaginary part of f are both harmonic. And also, harmonic functions apparently turn up naturally in physics, in physical situations. I have some stuff written down there, you can read it if you want. But, okay, we also have this definition. So if you have u, and this is a little bit different from the definition I gave last time. So last time I gave the definition in the book, but I think this one is actually more standard. So you have a harmonic function. Any harmonic function v such that u plus iv is analytic on E is called a harmonic conjugate of u on E. So here's some harmonic function. If there's some other guy such that I times that other guy added to u makes an analytic function, then that guy is your harmonic conjugate. So the natural question to ask is, when is one guaranteed a harmonic function, harmonic conjugate? Suppose you have a harmonic function, you're wondering, is it possible for me to get a harmonic conjugate for my function here? And the answer, one answer, this is from a book by John B. Conway. I think it's called Functions of Low Complex Variable. That a harmonic conjugate is guaranteed for all, is guaranteed if only if the domain is simply connected. The domain is simply connected. Simply connected means, roughly speaking, that it has no holes in it. Okay. It means that, technically it means that whenever you have a loop in your domain, you can deform that loop down to a single point. Okay. Within your domain. So, in other words, it's not, you can't have something with a hole in it, because then when you were trying to deform your loop, you get caught on the hole, and you wouldn't be able to deform it down to a single point. Okay, so that's the big theorem result. We're not gonna prove it. Let me give an example that sort of illustrates how problems might arise. So, example. So let's consider. This example I took right out of Professor Garcia's complex analysis notes. So just to give him credit, Stefan Garcia at Harmonic, who kindly lent me his notes a few years ago, on condition that I don't send them around. Consider this function on the natural log of the modulus on the complex plane with the origin removed. Okay, so it's not a simply connected domain. So we know we're going to run into trouble, or we suspect we're going to run into trouble. Okay. So if we think of this as a real value function, this is the natural log of x plus y squared. And then you differentiate. U sub x is x over x squared plus y squared. U sub y is y over x squared plus y squared. And then you differentiate again, and you see, easy to see, that u sub xx plus u sub yy is 0. So just differentiate again, and add them together, and you get 0. Okay, so it's harmonic, right? This u is harmonic. Okay, yes?
What do you mean consider it a real function? Isn't everything you did valid for complex?
Well, I'm just thinking of it as a function on the reals, on R2, right? I mean, you can think of this, right? This is u of, right? Should I think of this as a function of a single, should I think of this as a function of a single complex variable, or of two real variables? You can, it's sort of up to you how you want to think about it, right? So I'm going to think of it as a function, as a real value function, and then I see that it's harmonic. I mean, as a function on R2, as a function on R2, right? I'm sorry. I probably misspoke when did I say consider it as a real value function? I meant as a function on R2, rather than a real value function. It is a real value function. Does that make any sense?
Yeah.
Does that clarify?
Yeah. And should there be a square root or oh, it's just
yes. Yes, absolutely. Okay. So now, can we find a harmonic conjugate? So what would we need, right? Of course, we need ux equal v sub y, and we need v sub y to be negative ex v sub x. Right. For that to happen, that's what we need. So in particular, we need v sub y. We need v sub y to be u sub x, which is to say x over x squared plus y squared. Okay. So integrating with respect to y. And you end up with v of x1. It's going to be arctan y over x plus some function of x. v. Now consider v sub x. Right? We need u sub y to be negative v sub x. Right? Well, u sub y is y over x squared plus y squared. Negative v sub x, we take this thing and we get negative dx of the arctan plus function, right? Which, when you work it out, ends up to be y over x squared plus y squared minus c prime x. Okay. Anyway, the punch line of this is that c must be a constant. C of x has to be some constant, so you take it to be 0. Okay. And so what does that give you? That gives you that v is going to be arctan of y over x. Okay. Which is to say the argument of x plus iy. So that would work, but we can't use that as the harmonic conjugate on all of omega, because that function isn't continuous on all of omega. Right? As we go around the circle, when we come back to the original point, the argument isn't. It gives you the argument plus 2 pi. Right? So your function, this function isn't continuous, although you'd like it to be twice continuously differentiable. Right? So it doesn't work as your harmonic conjugate. You can't find a harmonic conjugate on the whole omega, right? But you could. We can find a harmonic conjugate on the complex plane minus some ray emanating from the origin. Right, because then you never have the trouble of going all the way around and coming back to the same place. Right, so if our omega were like this, minus the ray emanating from the origin, then we actually have found the harmonic conjugate. Okay, but you see what the trouble is and you see that this set is simply connected, whereas the other one wasn't simply connected. Okay. So the authors give sort of a local version of the version that is mentioned in Conway's book, and they don't prove it, but they just mention it. Say, if you have a harmonic function on some open set in a plane, then for any z0 in the open set, there exists a neighborhood in which u has a harmonic conjugate. Okay, and you see that that follows immediately from the other thing. It's a you need to do is take some simply connected neighborhood of your point, and then you have your guaranteed harmonic conjugate on that neighborhood. Any questions? Any questions? Yeah, Christian.
Does analytic imply that it's harmonic? Or is there any like
so-
relationship between the two?
So analytic implies that the component functions are harmonic,
Yeah.
right? But it doesn't. One doesn't. Because harmonic is really a statement about real value functions, not complex value functions.
Mm.
So- Okay, so there is this section on differentiation, but most of it is pretty trivial, so I'm gonna let you read that. So please read the section on differentiation, 1.6. I'll show you a couple of bits from that section, but most of it is basically like what I'm about to show you. So it's basically differentiating the elementary functions that we've seen so far. Okay, so you'll be pretty unimpressed by what I'm about to show you, and you'll be probably equally unimpressed by what you read. So e to the z is analytic. Okay, proof. You say, well, e to the z is d to the x cosine y plus sine y. So that's thinking of it as a function on R2. This function is uxy plus I dxy, where uxy is e dx cosine y, and dxy is of course e dx sine y. F as a real differentiable as a function from R2 to R2. As a function from R2 to R2, F is real differentiable, right? Because its component functions are infinitely differentiable. Since U, V are infinitely differentiable. Now you only need the partials to be continuous, but they're infinitely differentiable. So it suffices to check Cauchy-Riemann equations. Right? So then you differentiate these guys, and you see that they satisfy the Cauchy-Riemann equations. And then you see that with the derivative being e to the z. So it's pretty simple. Along the same lines, you can talk about let's talk about the principal law. So let omega be C excluding the negative real axis. And then the principal branch of the logarithm log z equals natural log of z plus I times the argument of z, where the argument is restricted to lie between negative pi and positive pi, is differentiable on a log. With the derivative of the log, of the principal value of the log, of the branch log, being non-divisible. And I'll prove this in a second, but let me just make a comment that you notice that we throw out, right? We throw out the negative real axis, for the reason that you may expect. The reason that you know that on that negative real axis, the function is no longer continuous. Right? If we throw that out, then our function is continuous, and then we have some hope of it being differentiable. But if we don't, then remember, as you come back, you're going to get the value with the argument that's 2 pi I bigger than before, and we run into trouble. So that's why you notice that we're the principal branch of the logarithm we're constraining to the open strip rather than the half closed, half open strip. Okay. So here's the proof of this. We know log's the principal branch of the log is the inverse of the exponential function, restricted to that strip. Right. Actually, let me put a circle on top to mean that I'm taking the interior of it. So the strip was half closed and half open. When I put the circle on top, I mean the open one. So that is, I mean, the strip where the imaginary part is between pi and negative pi. So not including the lower boundary as before. So, right, thus it must be the inverse guaranteed by the inverse function. The inverse function theorem guaranteed us, that e to the z, right? That's non-zero everywhere. So you're going to have a local inverse. Well, here is your inverse, so this must be it. Right? And so by the inverse function theorem, we know that the derivative of the log at e to z is 1 over the derivative of the exponential function at z, which is 1 over e to z. For all z in that open string. And so that's the same thing as saying that that the derivative of the log at any point is 1 over that point for all w in omega. The rest of the section is taking the derivative of the sine and then taking the derivative of the cosine. taking the derivative of so I'm not going to do it. Right? It's peanuts. Or as my wife says, it's a peanut. My wife is from Japan, and so when I told her about this expression, it's peanuts, she said, "Can you say it's a peanut? Like to be even less than peanuts." Okay. So more stuff. So it's all pretty simple stuff. Let's go through it quickly. Okay. So heading towards integration. In my other class, I took a poll based on a question that somebody asked me. It's a completely irrelevant poll, but maybe I'll do it in this class too, just to be humorous. How many of you have heard of Frito pie? Frito's pie? Frito pie? Only one person. Only one person? Wait, Adam, did you raise your hand? No. Okay. Only one person out of 9. Okay.
What is it?
It's yeah. So my friend who's from New Mexico said, "What? You haven't heard of Frito pie?" And I said, "I'm going to take a poll in my class and see how many people have heard of Frito pie." Anyway, it's something that you make. Apparently, you take a bag of Fritos, you cut it open, you put beans and chili and cheese on it, and you eat it. Yeah. And there are places that actually make and sell this.
I actually think I have heard of it.
Yeah, I've heard of it.
You have heard? Oh my gosh! So how many of you have actually heard of it, or even eaten it? What's
I
that?
thought you were talking about like a person or something.
Mr. Frito pie.
Frito pie.
Okay, so I guess maybe it's 3 out of 9. Okay. In the other class, it was like 4 out of 20. Anyway. Yeah. Yeah, I said, well, do people do this with Cheetos? And she said, no, that would be disgusting. Okay. Heading towards integration. So something we're going to do. It's going to be kind of dull going for a bit, I have to say. But once we get through this, then we can start doing Cauchy's theorem. So bear with me, and let's just get this started. Okay. So you have some complex value function. And let's say that it's continuous, or it just needs to be piecewise continuous, but let's say it's continuous. So piecewise continuous complex function. And let's say that W has real part U and imaginary part B. That W of T denote W restricted to the real axis. So T is a real variable, Z is a complex variable. Okay. And not surprisingly, what we mean by the integral over an interval of W is just going to be what you expect. You just integrate the real part, and you integrate the imaginary part, and that's going to be the value of your your integral of your complex value function on a real interval. So integral on some real interval of a complex value function. Okay. And so the basic, what you expect to hold, the things that you expect to hold do hold. Right? You have if you have a fundamental theorem of calculus, of course, right? So let W prime denote the real derivative W at t. So this is abusing notation, right? Because but anyway, we'll use it. If capital W prime equals W, and W and little w are continuous on AB, then of course you have the fundamental theorem of calculus, right? Then the integral of the little guy is going to be big W of B minus to big W of A, what you expect. And other basic properties hold, right? The integral from A to B plus the integral from B to C, W the same as the integral from A to C, W, etc. So basic properties hold. Something else that holds is the triangle equality. That the modulus of the integral is controlled by the integral of the modulus. So it held for real value functions. It will also hold for complex value functions. There's sort of an odd proof of it. Let me show that to you. So say that the integral is the integral of this complex value function is a complex number. Suppose this is the polar form of that complex number. Okay. So our goal is to show that R is bounded by the integral of the modulus, right? Because R is the modulus of this complex number. Okay? We're trying to show that the modulus of the complex number, the modulus of this integral is bounded by the integral of the modulus. Okay. Okay. So R is the same thing as e to the negative I theta times the integral. I'm just moving the e to the I theta to the other side. That's the same thing as the integral of w e to the I theta. I multiply by some constant. I can move the constant in, right? Because the integral is still linear. Right? And I can take the real part of that without changing anything because R was real to begin with. Right? So taking the real part of this thing is real. I take the real part of it, it doesn't change. R and right, this thing equals R, which is real. So taking the real part of it doesn't change anything. It's a real number. Okay. Now the real part of an integral is the same thing as the integral of the real part. And now I pull in the old, the real value triangle inequality. So now we use the real triangle inequality, real value triangle inequality. So the integral, right, the integral is controlled by the integral of the absolute value. But we know that that's smaller than the modulus of this. Which equals the modulus of that. Because e to the negative I theta has modulus 1. Yeah.
This first step, how is it that you can put in the e negative I theta in as e to the positive I theta?
I'm sorry, that's a mistake.
Okay.
These should all be negative. Thank you. Okay, any questions? Sort of an odd proof, but it works. Okay, upwards and onwards. Any piecewise continuously differentiable map gamma is called conjugate. So we're going to integrate, right, just now we were talking about integrating a complex function over a real interval, right, over a real interval. Now we're going to talk about integrating a complex function over a curve in the complex plane. Okay. Now the curves that we're going to integrate over are all going to be piecewise and continuously differentiable curves. We're only going to integrate over these contours. So here's how we define the so-called contour integral. It's sort of what you would expect, having been through multivariable calculus. So if you have a contour, and then you have a piecewise continuous function, then we define the integral of f over that contour. Okay. With respect to some variable, as the integral of f composed with gamma t, gamma prime t dt. So So this, with this definition, sort of the standard properties of integration still hold. Right? You have linearity. You have integral over. If you have a succession of curves, right? If you have like one curve and one followed by another curve and two, then you might as well integrate over the combined curve, right? This sort of thing. Let me do some examples. Let me do some examples to make this solid. So let gamma of t be e to the it, where t ranges between 0 and 2 pi. So this is describing the unit circle. Right? And suppose somebody asks you to integrate z over the unit circle. Okay. Well, by definition, that's going to be the integral from 0 to 2 pi of z evaluated at e to the it, and then we have the derivative of gamma, right? So the derivative of gamma is I e to the it et. You have gamma of t, you have gamma prime of t, gamma prime of t dt. Right? So that turns into I 0 to 2 pi e to the 2 it dt. And you just integrate that, and you get I over 2i 0 to 2 pi 2i over 2it dt, which turns into 1/2 e to the 2it between 0 and 2 pi, which is 0. So it's just like calculus. So just follow the definition. Just follow the definition and then calculate. Second example. Suppose you asked to do the same thing, but now for z bar. Well, now you're going to get the integral from 0 to 2 pi of gamma bar, right? So that's going to be e to the negative it, right? And then you have, as before, gamma bar. It's okay. I appreciate that you're sitting so far away. It was intentional, right?
Mm-hmm.
Right. Yeah. So what do you get? Right, these cancel off, right? And you get the integral of I. You get 2 pi I. So the integral of z, when you went around a full circle, was 0. But the integral of this other guy, when he went around a full circle, was 2 pi I. Third example. 1 over z minus z naught dz, where c is any circle over c, where c is any circle centered at z naught. Okay, so you could take, for example, well, gamma of t is going to be z naught plus r e to the it as t ranges between 0 and 2 pi. Okay, so you you're going over this circle. Here's a parametrization of the circle. Okay, and prime, of course, is going to be I R E T. And so when you work this out, this is going to be equal from 0 to pi over 1 over gamma of t minus z naught, write it out, gamma of t minus z naught, gamma of pi t. So it turns into 1 over r e to the I t, gamma prime, I r e to the I t, dt. So again, we get 2 pi I. Yeah, sure.
Is there any sort of intuition for this definition where you're taking the derivative of the path?
So, like you're taking f. This is just like the change of variable formula, right? If you think back to calculus 3, this is basically your change of variable formula. Right? You're evaluating the function at the appropriate point, but you also need some sort of scaling factor. Right? You need to throw in some scaling factor to make sure that you're integrating against the right length.
Mm-hmm. Wouldn't it be f prime at delta t times delta prime t? Derivative of the outside, the inside, times derivative of the...
No, because, so think like this, right? You've got gamma, right? Gamma goes into the plane. Gamma goes into the plane. F goes from here to here, right? So if I don't throw in the scaling factor, then I'm basically integrating over AB, right? I'm getting the wrong lengths. I'm evaluating the function at the right points, but I'm multiplying by the wrong lengths,
Okay.
right? And so you need this. This thing is the scaling factor to say that okay, this gamma maybe spreads out this first part more and the second part less, or something like that, right? Okay. So it's just your, this is just your change of variable formula. Okay, so coming back to the example again, right? We get 2 pi I, and let me ask you this: what happens if we go around? We go around the circle twice. What would I end up with here?
4 pi.
4 pi I. Right? Now suppose I go in the opposite direction. What am I going to have? Negative 2 pi I. Right? So this is, you can think of this, if I look at, for example, if I look at this, and this basically counts the number of times I circle z naught, right, in a counterclockwise direction. This will be relevant later on. Okay. Okay. Got 5 minutes. What should I do with my 5 minutes? Do one more example. So fundamental theorem of calculus for contours, for contour integrals. So suppose you have a contour, and you have f and capital F that are they're continuous functions, such that f prime equals f. This is the complex derivative. Then, as you might expect, the contour integral of little f can be evaluated by taking the difference of big F at the ends of the arc. And the proof is pretty simple. You'll see that well, you know, this by definition is the integral from a to b of f and t dt, which by hypothesis is the integral from a to b of f prime gamma t or gamma t dt, right? Which by the chain rule is f composed with gamma prime t dt. Right. And that gives you that this is f composed with gamma of b minus f composed with gamma of a by the fundamental theorem of calculus that we had earlier for complex value function, right? For on an integral. Okay. So the fundamental theorem of calculus for complex value functions on integrals gives us the fundamental theorem of calculus for contour integrals. Now, oh, you're late. Okay. Okay. So, for example, if we let gamma t be z naught plus r e by t, so it's again, you know, spinning around the point z naught. Then, if we consider the integral z minus z naught to the n dz. Okay, let's consider it. Well, this is going to be f of gamma 2 pi minus f of gamma 0, which is f of z naught plus r e to the 2 pi I minus f of z naught plus r e to the 0. Right? If f is an antiderivative of z minus z naught to the 0. And that will be equal to 0. Right? If there is an antiderivative then this is going to be 0, because you see we get f at this point minus f at this point, but they're the same point. So now notice we just saw that the integral of 1 over z minus z naught dz is actually 2 pi I. Right? It's not 0. Right? So what that tells us is that we can't get an analytic antiderivative of this on the full loop. On the full loop. And the reason is, of course, that the antiderivative would be the logarithm, right? And we can't make the logarithm analytic on the full loop for the same reasons we said before, right? Because when you come full around, you become discontinuous. It turns out that you can find antiderivatives for you can find antiderivatives for any other m other than -1, like the obvious antiderivative. But for -1, it doesn't work because your antiderivative won't be analytic on the full loop. Okay, that's where we'll stop today.